this lesson, we're going to take a look at what is arguably the most widespread of all enrichment technologies, gaseous centrifuges. Now, with the sole exception of the gaseous diffusion plant that's operating in Argentina, all large-scale enrichment operations in the world use centrifuges. And you may ask, well, why is that? Well, there's a couple of reasons. One, the technology is pretty basic. The engineering component of it can be somewhat complicated, but the physics principle behind it is quite simple. You just need to have access to some very specific underlying technologies in order to make this work. Second, if you'll recall, gaseous diffusion has a not so good separation factor of about 1.004. Centrifuges, on the other hand, especially modern centrifuges, have potentials that range from maybe 1.2 all the way up to 1.7 for the latest generation. So how do these things even work? Well, they work just like a centrifuge does. If you take something like a cylinder and you fill it with things that are of different densities, the biggest one that most people might be familiar with is those ones that they use in something like a medical laboratory for separating out the heavier components of blood from the lighter components. So basically you take those things, you put them in your cylinder, you spin it up to a very high velocity, and the heavier stuff is going to move to the outside and the lighter stuff will stay on the inside. And this is due to centrifugal force acting differently depending on the mass of the components. So in our simple little diagram that we have right here, we see that we're starting out with a generally fully mixed UF6 with our 238 and our 235 molecules just randomly distributed. Once we take, though, and start spinning up that cylinder on its center axis of rotation, what we're going to find out is that the 238 molecules, being slightly heavier, are going to want to move, generally speaking, towards the outside, while our lighter 235 molecules are going to want to stay more towards the middle. And by doing this, we're going to see that the mixture in the middle is going to be enriched. And now it's not perfect enrichment by any means, so we're still going to see a lot of U238 in there. But compared to something like gaseous diffusion, it is quite effective. Now, this is a more realistic diagram of what a centrifuge looks like. And I'll just go over the components here pretty briefly, and the ones that are, I would say, pretty important in terms of non-proliferation. Now, the bearings that we have that these things spin on, they're usually magnetic bearings, so what you would call frictionless bearings. And this is kind of important because the speeds, at the rotational speeds at which we operate gaseous diffusion, they're quite high. And the higher they are, the better our separation becomes. So normal bearings, because of just friction, would burn themselves out fairly quickly. So we use frictionless magnetic bearings. And that's kind of one of the key components to building something like a gaseous centrifuge. We have these things called baffles, which is being shown right here. And then we have scoops here, one here at the top, one here at the bottom. And the baffles are there so that when we try to pull out our product in waste streams, the baffles are designed in such a way so that it doesn't remix the material that's in the centrifuge, undoing basically all the work that you just put in. And the baffles are, again, one of these key technologies to having a successful operational gaseous centrifuge. The scoops also are designed in such a way as to make the operation quite efficient, again, not remixing everything. They are also one of the engineering challenges that needs to be overcome. This inner rotating bit, which is called the rotor, this is also an engineering challenge because you have to have a material that's strong enough to withstand being torn apart at high rotational velocities, but yet it also has to be not super dense, because the denser it is, the harder it is to try to spin it up, but it tends to maintain its rotational velocity a little bit better. Now, there's an outside casing to this, and every picture you've ever seen of a gaseous centrifuge, you're only ever seeing the outside casing. So you may ask, why is there even an outside casing? Well, it's not for to hide any trade secrets or non-proliferation reasons. It's there as a vacuum chamber. And that is, to put it plainly, if there was air around the spinning cylinder, then it would create drag and friction on that spinning cylinder, and it would be a lot less effective than if it had no drag. And that's all that outside cylinder is for, is to create a vacuum so that when we spin up the rotor, it's not going to experience any of those frictional drag forces from being surrounded by air molecules. All right, so let's get more into specifics. When we talk about gaseous centrifuge, the measure of how good they are is dependent upon this particular formula right here for a binary mixture. And it says that my separation potential alpha is going to be equal to E raised to the mass of our 238 molecule minus the mass of our 235 molecule times the tangential velocity squared over 2RT. T is temperature. Remember, our gaseous UF6 needs to be at least about 135 degrees Fahrenheit, usually a little bit higher. So it's around 239 Kelvin. R is a constant, so you don't really have to worry about that. The biggest thing that gives us our separation potential is the difference in the masses, which we can't do anything about. Those are set. So the only thing that we can change is this tangential velocity. And the tangential velocity is related to the rotational velocity by this very simple question, or equation, which is 2 pi r, where r is the radius of our spinning cylinder, multiplied by the revolutions per minute divided by 60. Now, when we look at these masses, again, this is the mass of either a uranium-235 or 238 atom, but then you have to add the 6 fluorine atoms that are around it. Okay, if you forget to do this, you get a much different answer. So velocity, how fast it's spinning, has the greatest impact on how good we're going to separate the material. So let's take a look at what does that mean in terms of numbers. Well, we have a bunch of materials here, starting with aluminum alloy and going all the way up to carbon fiber. So if we start looking at tensile strengths in megapascals, this is one of those determining factors on how good our material is. It's got to be strong to be able to withstand that high rotational velocity, which basically wants to take the material that our rotor's made of and basically try to deform it because it wants to push it further and further outside from that central spinning axis. So aluminum alloy, it's not very strong. However, it's also not very dense. So one measure of how good our material is if we take and divide our tensile strength by our density, and then we can go ahead and take the square root of that, we end up with the maximum speed possible that we can rotate it, or that maximum tangential velocity. So if we look at aluminum, we get about 327 meters per second tangential velocity, how fast it's spinning. If we look at something like titanium, which you would think would be better, right? Just common knowledge that titanium is better than aluminum, we find out, not so much. It has a higher tensile strength. However, it does have a higher density as well. So we end up with a max tangential speed of only 310 meters per second. Now, these are just kind of common alloys of this material that I looked up. There are specialized alloys that have better numbers than these, but I just wanted to give you something that was a typical representation of what these materials are capable of. Now, if we look here at something called miraging steel is incredibly strong. In fact, it's got the highest tensile strength out of all the materials here on this table of almost 2,700 megapascals. But it's super dense. It's about 8 grams per cubic centimeter. So if we take a look at this maximal rotational speed, we see that it is actually much higher than both aluminum and titanium at about 580 meters per second. Now, miraging steel is one of those export controlled materials which is very specific to things like this, like gaseous centrifuges. In addition to, again, those engineering things I spoke about earlier, the baffles, the scoops, the magnetic bearings, these are all integral to creating a gaseous centrifuge for uranium enrichment. And these things are kind of controlled pretty heavily. And we'll talk more about the control regimes and export lists and that sort of thing a little bit later on in the class. Now, as impressive as miraging steel appears, let's take a look at something that's even better. And that would be glass fiber, or as we know it, fiberglass. Very specific kinds of fiberglass, mind you. This isn't stuff you can go and roll down to Home Depot or you know, your local building supply store and get this stuff. If we look at its tensile strength, it's pretty high, 1500, with a pretty low density of only about 2.5 grams per cubic centimeter. So these two things combined give us a maximum rotational speed that's far above anything that we can achieve with miraging steel, which is about 775 meters per second. So this is a huge improvement once again. So we've made a huge step up from aluminum/titanium to miraging steel, and now we're making another huge step up to glass fiber. Then we go to the wonder material of the past couple decades, which is carbon fiber, which, as it turns out, has a higher tensile strength and a lower density. So what we're seeing here is the values that I pulled for both the glass fiber and the carbon fiber, again, may not be representative specifically of the materials that are used to construct these gaseous centrifuge rotors, but we'll call it close enough for all intents and purposes. And we can see that it's 956 meters per second. And these are like current numbers of what I would say is more modern carbon fiber than what we would have seen even 2 decades ago. And so this is what's possible now. And so with this incredible increase in rotational velocity, our alpha is going to likewise increase by a pretty significant amount. Now, what happens if you exceed these maximum peripheral speeds? Well, as it says on the slide, it kind of goes boom. They will deconstruct themselves rather rapidly, and what you end up with is a high-speed mass of rapidly outward expanding shrapnel. It kind of turns them into a bomb or a grenade. So you never want to, not only do you never want to exceed that max rotational velocity, but generally speaking, you don't actually even want to hit it. You want to stay a little bit back from it to allow for a safety margin. So let's look at it a little bit differently as a chart. Now this is for a cylinder with a set radius of 10 centimeters, which is, it's pretty close to what's actually used. So if we hold the radius at 10 centimeters, then the only thing that's really going to change, because the masses of the 238 and 235 molecules are the same, we can say that the temperature is going to be locked at some given value. Of course, R is a constant. What we can see is how do we change our alpha value with not only our tangential velocity, which is a very important number, but with RPM, because most people, the tangential velocity may not be something that you readily have an image of in your mind, but almost everybody understands what RPM means, or revolutions per minute. So let's go ahead and take a look at alpha with RPM. Okay, so we have two different axes here on the Y, our tangential velocity and our alpha, and while we have our RPM here in the middle. Now, tangential velocity is directly related to our RPM, so that's this straight line right here. Okay, our alpha, however, because it's an exponential term, is going to be this curved piece here. So when we talk about RPMs of a gaseous centrifuge, we're starting down here at 10,000 and just moving up from there. And so as we increase in RPM, we see very little gains at the bottom. But as we start to really ramp up that speed, 40,000, 50,000, 60,000 RPMs, we start going from 1 to 1.1 separation all the way up here at 80,000 RPM to almost a 1.5. And again, this is just an example. This is not indicative of any particular centrifuge technology or centrifuge design. Just something to give you an idea that, first of all, the rotation, these things are spinning incredibly fast, hence the need for the magnetic bearings. But we can see that its RPM, or tangential velocity, directly affect how good our centrifuges are at separating out our uranium into our enriched versus waste streams. So in the next lesson, we're going to take a look at the last of the what I'll call the gaseous methods, which are the aerodynamic methods, only one of which was ever used in the real world.